We're going to talk about related rates and solving problems where we have to take the derivative with respect to time, right? So that's what this related rates is about, is things we're going to dt. Okay, so we're going to ddt both sides of an equation. And why would we want that? Well, we might want to have, as we're going to do in our first problem, actually, water, the rate that water is draining out of a cup or something. So let me just draw a cup. And water is dripping out of a cup. And we want to know what that rate is, right? So that rate might be something like cubic inches. Let's say it's 3 cubic inches per second, which is actually a ton of water. It's a big cup. So 3 inches per second, 3 inches cubed per second. So this is a rate, and that rate is not dy dx. It's not the slope of a line or parabola. It's actually the rate of change of the volume with respect to time, right? And I would put 1 second here, or maybe we'd put a higher number here, but 3 inches cubed per 1 second, right? So that's the rate of change of volume every 1 second, with respect to time. Every 1 second you lose, in this case, so let's put a minus here actually, 3 cubic inches of water per second. All right, so that's dV dt. So everything we're going to be doing with related rates is with a delta t, a change in time. Okay, obviously, just like in slopes, we could write -6 inches cubed per 2 seconds, right? Per 2 seconds. And again, that's the change in volume, and this is the change in time. Okay, change in volume over change in time. So that's why we're going to do this. We're not going to do dy dx, or we're not going to do d dx to both sides. We're going to do d dt. All right, and if we're going to do the volume formula, which we'll do in the next problem, you'll see how that works. So let's go to our first problem. And what I've done here is I'm going to show you the steps on the left side here and actually do an example using these steps so you can see exactly what we mean. So we'll talk about each step and then we'll apply it to this particular problem. Okay? So let's read the problem first of all. And the problem says a cylinder. Okay, so the first thing I'm thinking about is a cylinder is my formula. That's going to be here. We need a formula. Cylinder filled with water has a 3-foot radius and a 10-foot height, which you can see from the diagram. It is drained such that the depth of the water is decreasing at 0.1 feet per second. How fast is the water draining from the tank? Okay, so a couple of things. The first thing we have to identify is what are they asking for, right? And that's also going to be down here. Obviously, my last step is I want to solve for that variable. So what do I want? And 99.9% of the time, if not 100% of the time, that's going to be a rate, right? This is going to be a rate. What rate do they want, okay? And usually, as you know, with questions, with word problems, it's usually the last sentence. So the last sentence is here as, how fast is the water draining from the tank, okay? So I know it's dt, and the water is going to be volume. I want to know how much volume, so it's going to be dV dt. Okay? So that's what they want. Put that over here. And I like to put a question mark there so that I know that's what they want. And what do you got? Now this is New Jersey speak for anybody not from New Jersey. What do you got? So I've got to see what they've given me. And as far as a rate goes, they've given me this, decreasing at 1.1 feet per second. See this per? That's very key, that you have a rate. That per tells you you've got a rate, okay? And what's changing at 0.1 feet per second? The depth, okay? And what is the depth referred to? H. So what they've given me is dH. I usually use small h, so you may see me change that. dt is, and it's decreasing, that's very important here, so we're going to use a negative, is negative 0.1 feet per second. So depending upon your perspective, sometimes it's going to be negative, sometimes it's going to be positive. If we're looking to see how something else changes in another different problem, but it's going to be negative because we're draining water out and we want the h to get smaller over time. And this will decrease the h over time. Every second, it'll drop by 0.1 feet. So we want to see how much water we're actually losing. So that's your first step. Your first step is just to identify what do you want and what do you got. Because these two quantities are going to drive step 2, and it's also going to drive the final step down here with solving for the particular variable. So in the end, we're going to be solving for this variable dv dt. Okay, the next step is write a formula. See, we're going to create a formula, and then we're going to take the derivative of it. So we need a formula that relates this. Well, it's a cylinder, as we saw earlier. It's a cylinder, and it's volume, the volume formula. So my formula is going to be V equals base times height, right? Base area pi r squared times height. Okay, so that's steps 1 and 2. And now step 3 is very important. It says get rid or substitute out. This is substitute. Get rid of, this would be an of here, of variables that aren't wanted or given. See step 1. So in other words, I don't want anything other than v and h in my formula. It's very important. I only want v and h. Any other variables I want to get rid of if I can. Now that's different from a constant, right? So don't be thinking you've got to get rid of pi here. Pi is a constant. It's not going to be affected, and that's not a problem. But we do have a variable that we don't like, if you can look here, and it's r. Okay? So we would normally sub out that variable, but the problem is there's nothing to sub it out with. So for example, in this case, the radius is 3 and the height is 10, but that changes, that ratio of 3 to 10 changes as the water drains out. So we actually can't get rid of it here, okay? This is really only for variables that aren't going to disappear in step 4. So let's talk about variables that disappear in step 4. So there's no way to sub out this r. However, step 4 is also about subbing out variables, okay? This was nothing we could do about it. And step 4 is fill in any variables that don't change over time. So something that's rate would be 0. And that's what we have. If you think about this water draining, as the water level gets lower and lower and lower and lower, the h is changing and decreasing. In fact, I know how fast it's changing. It's changing by this much. But notice the radius doesn't change. It'll always be 3 all the way down. So the radius doesn't have a rate other than 0. It has a rate, it's 0. Okay, so dr dt is 0. So r is a constant throughout the whole problem. So it acts just like pi in the sense that it doesn't change. So we can substitute right away a rate of 3 because we don't have to worry about it changing. So I'm actually going to change my formula here to be v, let me use blue, v equals pi r squared h, right? And I'm going to put this 3 in there. So I'm going to put 3 in here. And of course we can just simplify this. So this is going to be 9 pi h, 9 pi h. Okay? Step 5. Let's do step 5. Step 5 says d dt both sides. Because remember, we're looking for rates with relation to time, with respect to time. So everything is changing over time. So we're not going to ddx both sides. We're going to d dt both sides. Okay? So I'm going to d dt. Don't forget the left side of this formula is volume. And we're going to d dt, the right side, which is what we just found here, right? Okay? So it's v, and this is 9 pi h. Okay, and when we do that, we get dv dt, that's the change in volume with respect to time, equals 9 pi, this is h to the first, so it's 1 h to the 0, but don't forget implicit differentiation, the chain rule, when we have variables that don't match with the respect to. So it's going to be 9 pi 1 h to the 0, so that's gone, it's just 1, times the derivative of this h with respect to t, so it's dh dt. So basically every variable is going to have some rate here. If it's not a constant like r was, it's going to have some rate, dh dt, dv dt, right? So you're never going to have a t in this formula so that you have a dt dt. You're not going to get that. Okay, so we're done with step 5. Step 6, fill in any given quantities at the time you want to evaluate. Now this is different. This is different than these earlier steps because this given quantity might be the height or it might be the volume. Now this formula this formula is completely independent of any variables other than the rates, right? Pi is a constant. So it doesn't apply to this problem, but there are problems where when you're done DTing both sides, you will have a variable left, r or h or v or some other variable. And the problem may say something like, when r is 7, what is the rate? Or when h is 2, what is the change in volume? So those are quantities at a specific time or at a specific place that you want to plug in so you can find the rate at a given time. In this step, given the quantities here, there is one quantity, of course, which is what we got, right? So what do you got? So the what do you got is here, and that has to go in here, okay? So remember, it's what do you want, what do you got throughout the whole problem. It's very important. On step 6, we're going to plug in what do you got, and then 7, we're going to solve for what do you want. So in this problem, dv dt is equal to 9 pi, and then of course times negative 0.1. And we're ready to go. Now, if you want to talk about units, which actually is very valuable here, this is, right, I'll use a different color here. This is feet per second. And if you remember where this 9 came from, right, this 9 was from the 3 squared, and the 3 was the radius, and the radius is in feet. So this is actually feet squared, right, feet squared. So when you multiply feet squared by feet, you get feet cubed. And that's exactly what I want, considering that I'm dealing with dv dt. I want feet cubed per second. Okay, so if you do some dimensional analysis on this, which we'll do in another episode, we will see that happen. But it's pretty easy to see in this very simple problem, right? So negative 0.1 times 9 is just 0.9 pi. And it's feet squared times feet over second. So it's feet cubed per 1 second. And that's it. Okay, now try this problem and we'll go over it in class. Now, remember, you're looking for what do you want and you're looking for what do you got, right? And some of the key giveaways is the units, right? So this is meters squared per minute. So see if you can figure out what that is. And of course, this is what they're asking you for. Okay, and as we mentioned earlier, sometimes in step 6, they give you quantities, right? They give you quantities, right, for variables. So there we go. Notice that is not to be used in step 3. I'm sorry, in step 4. That's not to be used in step 4. So give this problem a try. You've got all the steps right here. Keep that open, and then we'll go over this in class.